What's going on, everybody? Welcome to another video. Today we will be talking about the Central Limit Theorem, and the question that we want to answer is, what is the sampling distribution of the mean? Now, a sampling distribution is the distribution of sample statistics computed for different samples of the same sample size from the same population. The best way to dissect this is through an example. So let's suppose that you are interested in estimating the mean number of hours Americans watch TV per week. Now, obviously, you can't collect information from all Americans. So instead, what you do as the investigator, you go out and you randomly sample 100 Americans, let's say, and find the sample mean to be 10.4 hours. And what we're going to do is, let's say that you repeat this process 10,000 times. Um, we're going to assume the population mean mu is equal to 10, meaning if you were to get information from all Americans, the true average number of hours would be equal to 10, and x bar is an estimate of mu. X bar is a random variable, so it's going to vary from sample to sample. And so we iterate 10,000 times. Each time we take a sample from our population, we calculate the sample mean, and then we record what that sample mean was in our sample means list. And what we're looking at is we have 10,000 estimates of mu. And the question is, how reliable are these estimates? What is the distribution of these 10,000 estimates of mu? So what we're going to do is we're going to go ahead and construct a histogram of all of these sample means, and here is the result. As you can see, the distribution of sample means is bell-shaped. The center of the distribution is equal to 10, which is mu, the population mean. And it is also true that the sampling distribution of x bar has less spread and is less skewed than the population distribution, which is a pretty powerful result. If we were going to formalize this with a definition, what we're saying is if you have n independent observations collected from a distribution with expectation mean, mu, and variance, sigma squared, then the distribution of x bar converges to a normal distribution with expected value, mean, equal to mu, and variance equal to sigma squared divided by n. So what's really cool about the variance is that as the sample size increases, the variance of x bar, how much uncertainty there is in that sample statistic, starts to approach zero. And that makes sense because as your sample size increases, you're pretty much approaching the entire population. And by the time you get information from the entire population, there's no uncertainty in that estimate. So this is pretty intuitive. And as long as you have your independence assumption and it holds, proving these results is pretty straightforward.